All right, my chem buddies here, back into 14.2, third lesson to try and get through chapter 14. As we go look at this one a little bit more closely, in the last video we analyzed this guy right here and realized that we could defend with the entities method, down here, why we have electrons moving from anode to cathode. Zinc ended up being our SRA, copper 2 plus our SOA, and so this had the pull for those electrons and yanked them all the way over. All right, so now we have this electron transfer between RA and OA. It is a spontaneous reaction, so it will actually happen. We need spontaneity to make a voltaic cell because a voltaic cell, as one of its definitions, is that it is a spontaneous flow of electrons. A battery would suck if it didn't spontaneously give us electrons to run our devices. So let's take a closer look at what is actually happening. As we take a closer look here, in three parts, we can break down this voltaic cell, and it is this simple, guys. We must have an SRA that gets oxidized, and in this case, it is zinc that is facilitating that for us. Zinc is the source of our electrons. By definition in chemistry, the anode is always the site of oxidation. So we didn't know which was anode and cathode until we did our analysis of the entities and figured out which one was the SRA and wanted to give up its electrons to a competing SOA. So zinc is converted to zinc ions. Here's a neat little side effect of your batteries and one of the reasons why they die. Your zinc is being consumed. Zinc loses mass because if you look at the half reaction, you have elemental zinc, the electrode, turning into zinc 2 plus ions, part of the solution with those extra electrons. So the anode will lose mass all the time. The SRA will always be the anode, get oxidized, and lose mass. Zip down to the picture at the bottom of the page. We'll take a closer look here. And if you take a look at your zinc, all right, you can see that as an atom of zinc loses those electrons, and there they go, they're moving up to the wire to be consumed or taken by the copper 2 plus, then you're left with a zinc ion in its wake after you give up those two electrons. So you can see that we're starting to lose bits on the anode. And if you take a look at this one right here, there's your zinc anode after running for an exceptional amount of time. You can see what was in the solution, what wasn't, and yes, we did lose mass on that one. So that is an interesting little side effect that happens. All right, for the second part of your problem here, we have to find the SOA because it's still redox, it's still two half reactions, it's still a movement of electrons from oxidation to reduction, or SRA to SOA. So copper 2 plus is our SOA. Therefore, we move the electrons through the cathode, but the copper metal here in this case is really just helping facilitate, bring the electrons into the solution so that the copper 2 plus ions can actually access them. So it is your copper 2 plus that is your SOA, and we find a reduction to solid copper. By definition then, and this is again how chemistry will look at it, reduction always occurs at the cathode. Oxidation anode, reduction cathode. Please, please, please remember that. Since what we are giving electrons to copper ions in solution, we are going to make solid copper. Well, where's the source of these electrons? It's on the copper surface. So copper will be deposited at the cathode, and the mass of your cathode will increase. You will start to get heavier and heavier and heavier. Again, another reason why we see less efficiency in batteries as they run over time. So, by definition then, SOA will always be the cathode, it will always get reduced, and it will always gain mass. All right, interesting side effect. Again, if we zoom in again, all right, you can see that as those electrons come down through your wire and into the cathode, they can be given to any ion that bumps into the surface, causing a change into an atomic form, in which we would start to see this plate upon your cathode. Take a look at the picture and look at what happened to your copper as it ran over time. You made more copper at the expense of zinc One got lighter, one got heavier. The last part, and this is one that, kind of gets forgotten here, is this purpose of the salt bridge. The salt bridge completes the circuit pathway, but not for electrons. Remember, the electrons are being released here and gained here, so they only exist for half the circuit. This is going to cause some problems in our two half cells. If we were to take a look at the one down here, all right, what you're doing is you are producing a whole bunch of positive ions in this solution. If I start to allow this solution to become positive because of all those zinc 2+ ions, these electrons are eventually going to start being pulled back towards the significant positive liquid that is being created. We don't want this to happen. So in our salt bridge, we have a source of positive and negative ions that will not participate in the reaction. As this becomes more positive with zinc 2+ ions being created, chloride ions will migrate, zinc 2+ ions will migrate, and we make this ionically neutral so that electrons still want to move one way in the circuit. Neat, huh? So for this one, what's also happening to my cathode or my reduction half cell? Copper 2+ ions are being consumed and making elemental copper, which means I'm losing positive charge in this particular solution, and it would start to become negative if I did nothing about it. If this starts to become negative, electrons would lose their willingness to come over and migrate towards a negative solution. They would start to feel a repulsion away. So again, the salt bridge does a couple of things. It offers a way to bring positive ions in that would not react and move some of the spectator negative ions out, maintaining a neutral solution here, and again, facilitating that electron flow. So, if the solutions are not neutral, they begin to accumulate ionic charge and impede electron flow. We don't want this, so the salt bridge is used to help maintain solution neutrality. Again, this would be hugely impractical in any sort of actual battery you might want to use, having all this glassware and liquid and so on and so forth. But to really look at what is happening and how we make a battery work, aside from other technologies that make it more convenient to use, this is essentially what's going on. Electrons move from Ra to OA, and within these solutions, as we have an ionic and elemental transfer, we need something else that is going to help maintain my electrolyte solution's neutrality. There you go. We can look at a couple more examples in the next lesson. The textbook does talk about this, so I should probably finish off with this idea. Soka-jerk, it's just an acronym to try and remember what's happening in your voltaic cell, but the strongest oxidizing agent is the cathode. Therefore, gaining electrons and reduction happens at the cathode. So it's just trying to remind you of at least one half of this reaction. All right, use it if you like it, forget it if you hate it. See you in the next lesson, kids.